Okay. Now for something completely different. All right. So I have a semi-legal copper pipe right here. This is what copper shower pipes used to be like. They were really big. Because you can't make them this big anymore because for water conservation, they have to make new houses with thinner shower pipes. Pretty cool. But I got one of these. And it's just a copper pipe. Now, do you know if copper is magnetic?
Yes.
Okay, let's take a look. So, to navigate around chemistry here. So I got some really strong magnets. Crazy, crazy strong magnets. And I'm gonna, okay. So this is a steel bolt, very magnetic. Okay. Copper, not magnetic. And if I put the steel bolt in the copper pipe, something kind of interesting happens. So I'll put the steel bolt in the copper pipe, and I can hold it in there with the magnet. Okay. So definitely a magnet. Steel, very magnetic. Copper, not so much. Copper's not magnetic. Okay, now we're going to do something interesting. I'm going to put my steel bolt down the tube. Okay. Everyone be very quiet. Count how long it takes for the steel bolt to fall not quite 2 meters down the pipe. Ready? How long does that take?
1 minute.
No, not quite 2 meters. Probably about about a second, maybe? About 1 second. We could do D equals 1/2 AD squared to find out how long it takes to fall. So there goes my steel pipe, or steel bolt. Then we do the same thing with magnetized material, about the same mass, about the same size. The magnet's about the same size as the bolt. They're almost identical mass. Count how long it takes the magnet to fall. There it goes.
11.
There's something in there, right? You're gonna like bolt right through. Magnet. It's dancing around in there. No, it's not spinning. It's just kind of cruising down the way. There it goes.
I don't believe you, Sean.
It's science.
Want to put something else down there?
Cheeto.
You're like, it's good to put a Cheeto in there. Okay. Count how long it takes the Cheeto to fall.
Pretty fast.
That's how long. The Cheeto falls pretty fast. So yeah, it's much like the bolt, which is not magnetic. Yeah, so it just falls right through. Yeah, you Cheetos. And we can put all sorts of fun things in there, but it's not going to change the fact that if you drop something down the pipe, it pretty much falls like most things fall, in like free fall. But when you put a strong magnet down the pipe, that's no longer the case. It doesn't fall like it's in free fall. Something is crazy and reducing its velocity. What do you call something that reduces velocity? So what does a parachute do to slow you down?
It catches air.
And it produces a what in the upward direction? Drag, which is a what?
Force.
Force. So there's a downward force pulling on. Now if I drop, just make sure that you think it's not a magic magnet. I mean, you're like, that's a magic magnet that doesn't normally fall with gravity, so it's an anti-gravity. Just make sure it's not an anti-gravity magnet. It does fall like normal. You know, like it falls, so it's not an anti-gravity. It's going to fall at the exact same rate as the bolt falls in the absence of a big magnetic tube. That's just a copper tube, which isn't magnetic.
What?
The copper tube isn't magnetic.
But it still has a magnetic.
Yeah.
If the copper tube was bigger around, would it go faster? Like further away from the copper?
If it was a thicker magnetic, or if it was a bigger tube, if it had a bigger diameter,
Yeah.
would it fall faster? Probably. Because we're going to find out that the thickness of the copper tube is actually does play a part. But so just like a parachute slows you down as you fall, that slows the magnet down as it falls. So there has to be some sort of force pushing against the weight. Now both of these have a weight, and they're about the same. The bolt and the 8 little green magnets they have are about the same. They have about the same weight, so they have about the same force pulling them down, so they have about the same acceleration, about -10. But when I drop this one through the tube, nothing happens. When I drop this one through the tube, it slows down and takes a long time to fall. So there's an upward force. Anyone know where that upward force is coming from?
The ground.
The ground. Magnetic field. I'll tell you in a little bit. I'll tell you a little bit where it's coming from. So today we're going to start learning about magnetism. And magnetism is pretty cool. It's what gets us to where we are. If you had no electromagnetism, you have no power coming out of the dam just down the way. If you had no electromagnetism, your phone doesn't work. Your car doesn't work. You can't start your car without electromagnetism. Unless you have a crank, I guess. Most of us don't have a crank. We have something called a solenoid. So we're talking about magnetism. Where does the magnetic field come from? Where does magnetism come from? It comes from flowing electrons. Magnetism comes from flowing electrons. It turns out when electrons move, they create an electric field. Now we've encountered this. We learned about current and we learned about electrostatics. When you have electric charges, they create electric fields. Well, there's those electric fields, it turns out. Hans Christian Oren looked at it and said, oh, those electric fields actually create magnetic fields too. Something kind of interesting happened. And there was this guy named Ben Franklin. You ever heard of Ben Franklin?
Who is that?
What did that guy do?
He wanted a national turkey.
He did what?
$100 bill.
$100 bill.
He really loves him.
You might be familiar with an experiment. There was a kite and a key, and he tied the key to the kite string, and then during a lightning storm, he touched the key and he got a little shock. He's like, hey, lightning must be electricity. Something more important was actually happening that they don't teach you in the elementary school textbooks. Turns out, he had a compass. He had a compass, like one that one might take with them when they go hiking, so they know what direction is north. And every time the lightning struck, the compass spun. He's like, that's weird. I know that my compass is going to follow it's going to follow the magnet. You see the little compass arrow moving around?
Yeah.
So watch this.
What the heck?
Can you see that? Do I need to turn the lights on, or can you see that? You can see it's like.
Doesn't that break the compasses?
I guess it might if we put too much force, we could actually break the little pin in there. But yeah, so compasses are lined up to magnetic fields. Did I break it?
Is that how they work?
Follow me, compass arrow. Well, it turns out he had his compass, and he's just like, okay, that's cool. This way I can find my way back home. And there was a lightning strike, and the compass needle spun. It's like, oh, that's weird. So there had to be some kind of connection between electricity and magnetism. And it turned out, or pointed out, it turned out it happens when electricity moves, when electrons move, they create electric fields. Those electric fields create magnetic fields at 90 degrees to the electric field. So if the electric field is going this way, the magnetic field is going this way at 90 degrees. Realize I'm saying this way, it's a two-dimensional phenomenon, three-dimensional phenomenon. It's kind of hard to explain what it is at a three-dimensional phenomenon. Yeah, that's where the right-hand rule comes in. We'll get to that. Okay, so that's what magnetism is. Oh, yes. What do traffic lights and vending machines have in common? We'll get to that. It's pretty cool.
We get really mad when they don't work right away.
That's true. They frequently break down. Okay, so if you got a bar magnet, I don't have a bar magnet handy, but if you got a bar magnet, there's a North Pole and a South Pole. Where do these poles come from?
The core.
The core?
Yeah.
Yeah, they come from the core. we're basically sitting on a gigantic magnet. The Earth is the biggest magnet that we know of.
What about other planets?
We haven't actually found any. There are bits and pieces of stars that have magnetic fields, but as far as planets go in our solar system, we are the biggest. We are standing on the biggest magnet in our solar system, the big magnetic field. But where does the magnetism phenomenon come from? Spinning what?
Spinning magnets. Spinning core.
Spinning.
Yeah.
What did I say?
The
It has to.
revolutions of
What
the
did
Earth.
I tell you creates a magnetic field?
Domains.
Electrons. Good. Electrons moving create electric fields. Those electric fields create magnetic fields. So it is the spinning of electrons, particularly the non-symmetrical atomic electrons, and I'm not going to go into all the crazy quantum about why some things are magnetic and some things aren't. It is kind of cool though. If you look at the periodic table, you'll find chromium, manganese, and iron and cobalt. Those are your magnetic metals. Primarily iron and cobalt, but chromium and manganese a little bit too. But primarily iron and cobalt, those are your magnetic metals. They're right here. Chromium, iron, cobalt. Nickel helps a little bit too. Nickel can be magnetic as well. And then alloys of these guys are the metals that we usually use to make magnets. So it is the spinning of electrons that creates little tiny magnetic moments. And if you get enough of these magnetic moments together, they create a cluster called a domain. So if you were to look at this magnet and zoom in, what you would see, if you were to zoom in at the atomic level, you would see a bunch of these domains that are all aligned in one direction. In other words, the electrons are spinning in one direction. Now realize, this is a gross simplification. Let me explain what I mean. If everybody in this room pointed at that wall, everybody in this room pointed at that wall. If everybody in this room pointed at that wall, now we have an aligned domain. Now, everybody point in a random direction. Now we have normal material. But I know if I was to count all the directions, I got a hunch that there would be some direction that would be more than the other ones. Okay? If I all counted everybody's direction, north, south, east, west, there would be some direction just by the small sample we have that would be slightly more than the other one. There'd be like, well, there's 14 easts, there's only 12 wests, 11 norths, and 13 souths. Then the domain is pointing east. That's what's really going on at the atomic level. All of the domains in my copper pipe are random. And since there are billions upon billions upon billions of them, it's pretty much totally random. In a sample size like this, of the 25 of us that are in the room, if one or two people have one or two directions more than the other, then we would say it is aligned. In other words, in a magnet, of the billion or so atoms that are spinning around in here, 3 or 4 are lined up, giving it enough magnetic field strength. Okay? If you could get all the atoms to line themselves up in one direction, the material would fall apart. Does that make sense? So to say that all the atoms in the domain are aligned would be wrong. But there's enough of the atoms that are spinning in one direction to create a magnetic domain. Does that make sense?
So it doesn't take a lot of alignment to make magnetism.
Correct, yeah. If you had pure randomness, you have a non-magnetic material. If you have a few atoms that are lined up together, they create a domain, and those domains will become magnetic. Okay. But again, if you somehow, through some sort of science, were to get all the atoms lined up in one direction, the material would rip itself apart. It wouldn't be able to work. Okay, cool? Does that make sense? Because the bonding wouldn't work anymore, the material would fall apart. All right, so what we both basically boils down to is you have lined up magnetic domains, which are clusters of atoms. In unmagnetized material, you have perfect randomness. For every left, you got a right. For every up, you got a down. You got perfect randomness. The materials, all the atoms are vibrating. Okay, what happens when you cut a magnet in half? It makes 2 magnets, exactly. Because you can imagine a bunch of arrows pointing this direction, and by cutting it in half, you still have the arrows. Okay. The universe hates a monopole. A monopole simply doesn't exist. Monopole means one pole, a north without a south. a positive without a negative. To our knowledge, they don't exist. For every north, you have a south. For every positive, you have a negative. Does that make sense so far? Okay. Clusters of atoms make domains. Random, no magnetic domains. How do you make a magnet? Anyone ever seen these videos on YouTube or on TV?
You rub a nail
That works, yeah, rub a nail with a magnet. You have to align the domains. Now here's the crazy thing. Some metals are considered soft, where their domains can be aligned, and some materials are considered hard, where they cannot be domained, or they cannot be aligned. But this is how they make a magnet. In fact, you should probably go home and YouTube how to make a magnet. They show you, it's really cool. They basically take a material and they warm it up, and then they submit it to an extremely strong magnetic field. That aligns some of the magnets in a domain. When they take the magnetic field away, some of the domains will stick, and they'll stay that way.
Whoa.
Yeah. The best way to do it is do it when the material is warm. So you warm the material up so the magnets can move around a little bit, then expose them to a strong magnetic field. They line themselves up, and they stay that way. Like, I'm just dancing around, oh, magnetic field! Make it frozen that way. How do you unmake a magnet? Okay, question. Okay, yeah. How do you unmake a magnet?
Heat it up and then not submit to a magnetic field.
Exactly, you heat it up. You allow the magnets to basically rearrange themselves with complete entropy. So to unmake a magnet, you can heat it up or you can pound it, and that will reorganize, re-randomize the domains. The backyard scientist, I can't remember his name, the guy, backyard scientist on YouTube, he put a gigantic magnet and he poured liquid metal on it, and it was no longer a magnet. The heat was enough to randomize all the domains. The magnet was still a big chunk of metal, but it wasn't a magnet anymore. So, hey. Yeah, you re-randomize the domains. That's how you unmake a magnet.
So does that mean that magnets work better in cold?
Yes, that does mean that. Magnets do work better in cold because there's less molecular movement. In fact, there are some magnets that are superconducting magnets. When they get cold enough, they have no resistance whatsoever, which is something we'll talk about later. We'll talk about that.
Our core is a magnet, right?
I'm sorry?
Our core is a magnet.
Our core is a magnet, yep.
Then why is it
Well,
so
more
hot?
specifically, the solid core and the liquid mantle spinning around it creates a magnetic field. So it is the difference between the solid core and the fluid mantle that travels around the core that creates a magnetic field.
Why does it feel very hot?
The gravity of the Earth pulling all the material together, pushing everything together, produces a tremendous amount of energy. It's just like, it's like sandpaper. When you rub sandpaper on something, that friction exists. Well, kind of the same thing with all those metal molecules pushing in on each other.
Isn't the difference? Is that the difference? That's the difference.
It's the difference between the solid core, which spins with the same rotational inertia as the rest of the Earth, and the liquid molten core around it. That is that difference that creates a magnetic field. By the way, we'll actually get to that. It has a special name called the magnetosphere. Okay, so if you got some material and you got a paper clip, so paper clips are notoriously great for magnetic demonstrations. You got a paper clip. Now this paper clip by itself has no magnetic tendency. It can't pick up this bolt. But if I connect it to a magnet, then I've basically caused the domains in the paper clip to become aligned, and then it becomes a magnet. That's called an induced magnet. And if I take the magnet away, boop, the moment I take the magnet away, the domains in the paper clip then rearrange themselves back to randomness, and it's no longer a magnet. Fun stuff. So if you were to zoom in on a part of a magnet to see the domains, it's going to try to arrange the domains with whatever magnetic field it exists at the time. That's how you make a magnet. Okay, field lines. If I take my, actually you saw my compass, and my compass was like Let's line myself up. Okay, watch this. Here's my magnet. Look at the compass needle as it goes around. My head is in the way. Okay. Your giant head is in the way. Oh, okay, yeah, so there we go. So notice the compass needle is lining itself up with the magnetic field. Okay. If you drop a bar magnet in a bunch of compasses, they're going to line themselves up. They're going to go out, 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 over, 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 in, over, over. So they're basically lining themselves up. And they create field lines. Field lines are imaginary lines of magnetic field. Okay. And they curve. Okay. So if this is your magnetic field, it basically curves where magnetic field goes out from north and in towards south. Remember our electric field where we had positive charges that pointed out and negative charges that pointed in? Yeah. Same kind of deal. Same kind of deal. Norths point out, souths point in. So if you were to take a compass needle, it would point away from the north, it would point towards the south and towards the south. It would point in towards the south, and if you put it right here, it's going to point out. If you put it here, it's going to point this way. So it basically points like this. And this goes out till infinity. It gets weaker, of course, with distance, but it goes out to infinity. What do you think the magnetic field looks like inside the magnet? All going out. It's pointing out from north into south. Kind of like this. The opposite. Oh, it just looks like. It would just look like this. It'd be like having a positive charge. It'd be like having a positive charge here and a negative charge here. The field lines would just go straight across.
Is it always from north to south?
Yep. And we're starting to float into the formulas, and there's some really exotic formulas we'll be using. So magnetic fields vary directly with magnetic strength. In other words, the stronger the magnet, the more field strength there is. Which makes sense. Directly with current, if the magnetic field is being created with current, magnetic strength will vary directly with current, and then inversely with distance. So in other words, the further you go away, the weaker the field is going to be, which should make sense. And it's not inversely squared, which is interesting. It's just inversely. In other words, twice as far away, half as strong. Benson, are you with us?
Yeah.
Okay. Got my cool sunglasses on. I wear my sunglasses at night. Okay. Questions? I told the office staff to turn all the lights off in the main building so we could watch children bump into each other. I think would be hilarious.
Is that you from police? That might be an issue.
Yes, I know.
Okay, so the magnetosphere. Literally, it's actually called the magnetosphere. Magnetosphere is what protects life on Earth, and why, if we do colonize Mars, you'll still have to wear a spacesuit going out on Mars, even if there's an atmosphere. If we somehow terraformed Mars and there's even a breathable atmosphere, you would still not be able to go outside in shorts and a t-shirt.
Watch me.
Yeah, watch. You can do it once, or twice.
Well, you
but
can stay out there, but
you're basically the Earth is being blasted with what's called solar wind, ionized radiation. And one of the things we notice about magnetism, I don't have my TV anymore. If you ever take an old magnet to an old television or computer monitor, you can move it around and change the colors. Well, basically, what's happening. The Earth is basically blasted with solar wind, ionized radiation. But the Earth's magnetic field caused that radiation to basically miss. It's constantly missing the Earth. It's like having a big fan in front of you. You're like, you got this giant fan, you're like, I got this huge fan, and someone goes after you with a water gun. You're like, I'm gonna get you. I'm like, go for it. The water's never gonna make it. It's always gonna go around you or back at the person shooting. Same kind of thing. I'm like, I get you a water gun, like my fan. And that's what the Earth is doing. It's redirecting and deflecting solar wind, ionized particles. It's called the magnetosphere. It does that. Also, a fun fact is saying something called a magnetic declination. Basically, it's a magnetic boo-boo. It's the difference between true north and magnetic north. It's the difference between geographic north and magnetic north. I think it's 27 degrees. It might be 21 degrees.
oh wow.
20-something degrees. Yeah, it's considerable. So if you follow your compass, you're not going to end up at Santa's house. You're not going to end up at the North Pole. You're like, I'm just going to go north. And you're like, okay. You won't make it to the North Pole. You'll miss. End up in Greenland or something. And again, I wonder if Alexa knows. Alexa, what is Earth's magnetic declination?
Here's something I found on ThoughtCo. Magnetic declination, also called magnetic variation, is defined as the angle between compass north and true north at a point on the Earth. Did that answer your question?
No.
Thanks for your feedback.
I want to know what it is, exactly what. Oh, Alexa, how many degrees is magnetic declination?
Here's something I found from the article Earth's magnetic